In this segment, we're going to take up the idea of reaction stoichiometry. This is a really important topic. There's things related to this that we'll be working on for the next few class periods. And so it's really important that you get off on the right foot on this and that the underlying ideas make sense. Okay, so definitely try and make sure you pay attention and walk away from this one feeling like you understand what we've been talking about. All right, so our topic is reaction stoichiometry, and stoichiometry is very much a chemistry-specific word. Normal people don't ever say the word stoichiometry outside of chemistry, okay? What does that word mean? Stoichiometry is the chemistry word that really means something like how much, okay? And so any kind of quantitative relationship, how much or how many. So if you're reading a problem and if you can translate the question into how much of that substance is going to be used up or be made, how many moles, how many molecules, how many kilograms, anything of that sort is what a chemist thinks of as a stoichiometry problem, okay? The way we solve stoichiometry problems is, at least implicitly, by invoking conservation laws. Mainly the way chemists invoke conservation laws is by having a balanced chemical equation, okay? And so at the heart of every solution to every stoichiometry problem is making sure that you have a balanced equation for the reaction that's going on, all right? I made a note down here in the bottom, which talks about the idea of composition stoichiometry, which is, we could say that's sort of things we've been doing, right? Composition stoichiometry is really just when I say how many atoms of this element are in this much of this compound, or how many moles of hydrogen are in this many moles of water, things like that. We can think of that as a stoichiometry issue because it is a how much, okay? When I say reaction stoichiometry, now I'm talking about a how much question that also involves a chemical reaction taking place, right? A lot of the interesting work of chemistry has chemical reactions taking place because that's the part where we get to make new things, right? We get to create new materials, things of that sort. And so it's always important to know how much of the starting materials do we need to make enough of the product, things of that sort, okay? And that's what stoichiometry problems are all about. When we solve stoichiometry problems, the thing we do is we work with these reaction ratios or mole ratios, okay? So in this equation, this is the combustion of methane, right? CH4 is methane, nice simple hydrocarbon, okay? The primary component of natural gas. So if you have a gas burning stovetop, that's the main reaction that takes place when you light the burner. Reacts with oxygen, makes CO2 and water. This reaction has mole ratios of 1 mole of methane reacts with 2 moles of oxygen to make 1 mole of CO2 and 2 moles of water, right? Notice when we write the equations where the coefficients would be ones, we don't usually write them in there, okay? But there is always an implicit 1 in front of anything that doesn't have a number just sitting there in front of us. So we could say that I need to have 2 moles of oxygen for every 1 mole of methane. We could say that I make 2 moles of water for every 1 mole of methane, and so on. We can take any of those things in combination, right? So the coefficients that balance the equation are where these mole ratios come from. And those mole ratios are the things that essentially work like conversion factors to get us from how much of one substance is in the reaction to how much of a different substance is in the reaction, right? Over the course of this video, I'll do a couple of examples in slightly different ways that will explain what we do with these ratios. All right, this is a slide that you will see a few more times over the next few class days and videos, I suspect. And what does it do? It is the game plan for solving a reaction stoichiometry problem, okay? One step that I did not put in the slide there is the first step in solving a reaction stoichiometry problem is to realize that's the kind of problem you're looking at, right? So anytime you've got a chemical reaction taking place, and you've got a question that's asking you how much stuff either gets used up in that reaction or gets produced in that reaction, that's a reaction stoichiometry problem, okay? Being able to identify that idea, that's the first step towards solving it. Once you know it's a reaction stoichiometry problem, then really your next move should be to say, do I have a balanced equation? right? Because you always want to solve a stoichiometry problem starting with a balanced chemical equation. If you don't, then arguably you're kind of just taking a guess at it, okay? Yes, there are some simple problems that I could probably solve without writing down the equation, but they would really involve my just thinking up the equation and sort of balancing it in my head, which is probably cheating on that front, right? The next step says, the calculation you want to do wants to be centered on moles. What that says usually is you want to take the thing you know, the things you know, and turn them into moles. That's generally going to be the first step in a reaction stoichiometry problem once you've got your equation, okay? I think I'm up to my first step now, which is probably bad. How do we get things converted to moles? We've been doing that for some days now, right? So you could take a sample weight and a molar mass. You could turn those into moles. You could take a volume and density and turn that into mass and then turn that into moles. You could take, if you had a solution, you could take molarity and volume and turn that into moles. There's a whole bunch of ways to get things into moles, okay? So the general plan is going to be take the information we know, turn it into moles, use the balanced equation to get from moles of the thing we know about to moles of the thing that we're trying to find out. And then once we've got the moles of the thing we're trying to find out, at the end, we often have a conversion out of moles and maybe back into grams or back into volume or into whatever kind of quantity we're really asked to find, okay? And so one of the reasons why we do a lot in the first couple of weeks about just making you practice turning mass to moles and moles to mass is when you do these problems, you're going to have those mass to mole conversions. You're going to have a few of those to do just as steps along the way. They're no longer going to be the heart of the problem or the meat of the problem. So you really need to be able to do those kind of like their second nature, right? If it still takes you a few minutes every time you have to convert grams to moles to try and remember how to do that, then you're going to really struggle getting through one of these stoichiometry problems where you might have to do grams to moles 3 or 4 times before you're finished with the problem. Okay, so if you haven't gotten comfortable with those, it's an important skill to just get really confident that you just know how to do that and that you right away can dig in and get that done. All right, here's a relatively simple example. This is kind of a textbookish sort of stoichiometry problem, I guess. It says propane is the fuel in most gas grills. It's also the fuel in the gas range in my house because I live outside of the city limits and there's no natural gas service here. So the equation for burning propane is another combustion reaction, right? Combustion always means my hydrocarbon, propane in this case, reacts with oxygen, makes CO2 and water, right? The question asks me how many grams of oxygen are required to burn 400 grams of propane. So if I look at this problem, I can see a chemical equation in front of me, right? And I'm being asked how many grams. So it's a how much stuff question, and there's a reaction. So it's a reaction stoichiometry problem, all right? I've already got a balanced equation, so that was nice of the problem. It didn't just say, consider the combustion of propane. If it had said that, we would have had to write the equation first, but we have the equation. So what I usually do when I'm taking a problem of any sort really is I try and like strip away all the stuff that is kind of just around the edges of it and make it into a sort of a summary of what's going on. And this is my summary of this problem, right? It says I have my balanced equation. The thing I know is that I have 400 grams of propane. The thing I want to know is how many grams of oxygen do I need to carry out this reaction, all right? I always want to start with the thing I know and turn it into moles. So I'm going to start with 400 grams of propane, because that's the one thing I know. And I'm going to turn it into moles. That says I want grams of propane down here. And I want a mole of propane up here. Especially when I'm doing these reaction stoichiometry problems, I'm going to try really hard to force myself to write the propane after mole there, to say I've got this many moles of that stuff, because that'll help me keep track of things. All right, propane, let's do 12 for the carbons each, so that's 36. 36 and 8 for the hydrogens, that's 44 grams per mole, okay? So that is my, my moles of propane if I were to stop there. Okay, you can do these piecewise if you want to stop there. I have notes over here that tell me I get about 9.09 moles of propane. I tend to, because I'm, for obvious reasons, pretty confident I can do these problems, I tend to keep going. And you can easily get confident enough to do that too. I can assure you. The next step is I'm in moles of propane. This is the central step of my problem now, where I want to get from moles of the thing I know about to moles of the one I want to know. So that says I want to get rid of the moles of propane. My equation up here has 1 mole of propane in it. So I'm going to put, again, 1 mole of propane down here. I want to get 2 oxygen. It says my 1 mole of propane needs 5 moles of oxygen. So that's what I'm placing up on the top. If I stop there, I'll be in moles of oxygen, right? My problem didn't ask me for moles of oxygen, it asked me for grams of oxygen. So I'm going to hang one more step over here, which says that every 1 mole of oxygen is equal to 32 grams of oxygen. All right. And if I multiply all of that stuff out, my notes over here tell me that I need 1,455 grams of oxygen in order to pull this off and get my propane all to burn, okay? If you wanted to, like I said, I have notes, and if you like to do things piecewise, I can say if you stop there, you get 9.09 moles of propane, which after this step means I have 45.45 moles of oxygen. And then I multiply by the 32, and that gets me to my final number down here, okay? I like to do them kind of just all straight through there. It does probably help that I've been taking this course for the last 30 years or something like that. And so I'm quite adept at thinking I can set things up correctly, but I can go through here and make sure that all of my units except for grams of oxygen go away, which is the check that I've done things correctly. Right? So that's a relatively straightforward problem. In this case, I went from one of the reactants to the other reactant. There's nothing special about them being on the same side of the equation together. That just happened to be what we were asked to do. Okay. I think I'm going to do a second problem just to make sure that I make that last point. And this one says, what mass of sodium aluminum oxide would be needed to produce a kilogram of sodium aluminum fluoride there by the following reaction? Okay, this reaction actually has some practical uses, which I won't go deeply into right here. It's got what reaction? I've got hydrogen fluoride reacting with that sodium aluminum oxide. The important thing is I've got a balanced equation and I've got a how much question, right? And so that's what tells me that what I want to do is take the thing I know, that's my 1 kilogram there. I'm going to turn that into moles, and then I'm going to solve the problem. I think I've given myself another one of these set up the way I always do these, and so I'll write on this one. But I could probably have easily done this on the other slide as well. So the thing I know is that there's 1 kilogram here. So that's where I have to start, right? I have to start the calculation with something that I know the amount of, and that's the only thing I do know the amount of. I'm going to take my kilogram and I'm going to write it as 1,000 grams because that's what a kilogram is. I'm going to turn that into moles. That says I want grams of Na3AlF6 per mole here. And I have notes beside me that say that this is just about 210. And I certainly wouldn't know that molar mass, right? I would have to get the masses of the elements and add them up. I just did that already, and I've got it on the piece of paper sitting beside me, which is why I can just turn my head a little bit and find out what that number is. Now I'm in moles of here. I want to get from moles of the sodium aluminum fluoride to moles of the sodium aluminum oxide. So again, I get my mole ratio now. I want to get rid of the moles of this one. I want to get 2 moles up here of sodium aluminum oxide. If I stop there, I'm in moles of the reactant. I actually want to get grams of the reactant, so I'm going to put 1 mole of it down here. And then on the top, I'm going to, again, cheat from my notes over here, and my notes say this one is 81.97 grams in a mole. Notice a couple of things. Notice again, I deliberately, when I'm writing these things, I try very hard to make myself write moles of what substance. The reason for that is if I take this mole ratio and I just write it as 3 moles over 1 mole, immediately it becomes much easier to put it in upside down. okay? And I want to make sure I get it right. And this gives me the opportunity to go through and just kill off my units of things. My moles go here and there. These moles go here and there. I'm left with grams, which is where I wanted to get. And I have notes over here that say this is about 1,171 grams of my sodium aluminum oxide. So you might remember probably in our very first actual live class meeting, I made a comment that you could do an awful lot of the problems in this course by thinking about them as converting units. This is the kind of problem I'm thinking about when I say that, right? Because every one of those steps is a little bit like doing a unit conversion, right? The first one is turning grams into moles. I'm still looking at how much of the sodium aluminum fluoride do I have. When I get to the next step, I'm turning moles of one thing into moles of another, right? I'm using this ratio that tells me they have to be in this case, 3-to-1 ratio, right? So that moves me from moles of one substance to moles of the other substance. And then lastly, I do another mole to gram conversion on the way out, right? Those couple of example problems illustrate a few things. Number one is these kinds of problems are really just full of mole to mass, mass to mole conversions, right? So you just need to be good and efficient at those, right? They shouldn't slow you down. You should just say, I just have to do that, right? Number two, if you keep track of units, they help you through things quite a bit in getting your quantities in place, okay? The other thing I tried to point out here is in this example, the two things I'm working with, I started with a product and I went to the amount of a reactant, right? That makes no difference whatsoever in how I solve the problem. Okay, all it does is it says which mole ratio am I going for, right? If I had asked how many grams of the HF did I need, then instead of having a 3-to-1 mole ratio, I would have had a 6-to-1 mole ratio. And then I would have had to convert moles of HF into grams if that was what I was trying to find, right? So we can really do this same calculation for any pair of things, no matter where they are in the equation, whether they're both on the reactant side or both on the product side or one on each. That part makes no difference whatsoever. So try very hard to think of those as still being the same kind of problem. One of the things that makes this course hard for some students is if it starts to feel in your head like there's 27 different kinds of problems you're supposed to be able to do, right? If you can make a lot of problems that at first glance seem different, feel the same, then it's much easier to get confident that you can do things.